Alright, this is probably the most challenging problem of the four business-related problems in terms of applications of calculus. And in this particular problem, it's not the calculus that's a challenge, it's setting up the equation to do calculus on, which is the real challenge. And here's what makes this more challenging than the previous problems. We're given expressions about cost. We have v squared over 10, and I changed pounds into dollars because this is America. I've got v squared over 10 dollars per hour, and that's based on how fast the boat travels. So if I change my speed, if I increase my speed, it's going to increase my cost per hour. And I also have a fixed cost per hour of $62.50 per hour. And so if the question was asking find the speed which will minimize the total cost per hour, well, first of all, that would be a problem because the speed that would minimize the cost per hour would be 0, because the faster you go, the more cost per hour is going to be. But what they're actually asking for here is the speed which will minimize the total cost per kilometer. So that's what makes this problem a little bit more challenging. So the purpose of this video is to try to unpack this a little bit and see if we can make sense out of how to write the appropriate equation. This requires a little bit of understanding of rates, which is why we spent so much time studying rates in the beginning of the year. So the pieces come together if I just try to look at a sample. Like, let's suppose I fix my velocity at 20 kilometers per hour. How can I get cost per kilometer? That's my objective. And for starters, I'm going to take the given information and see what I can learn from it. So to begin with, we get the cost related to the velocity, and so 20 kilometers per hour squared is 400 divided by 10 gives me $40 per hour plus the additional $62.50 per hour, or a total cost of $102.50 per hour. But again, I need to figure out cost per kilometer. So in order to understand how to do this, I'm going to use a little bit of dimensional analysis. We know that we have dollars per hour, and we need to multiply it by some magic mystical rate, and that will convert into dollars per kilometer. So we want to keep the dollars here, but we want kilometers instead of hours as the independent variable. So just thinking in terms of dimensional analysis, dollars per hour times hours per kilometer equals dollars per kilometer, because what you should see is the hours divide out, and we are left with dollars per kilometer. So if you thought about that long enough, you may recognize that hours per kilometer is the reciprocal of velocity. Velocity is measured in kilometers per hour, and this is hours per kilometer. That's just the reciprocal of velocity. So let's put this together. All right, once again, we've got hours per kilometer times dollars per hour. And that's the hours per kilometer is the reciprocal of velocity measured in kilometers per hour. So all I have to do is take my $102.50 per hour, multiply that by 1 over 20 hours per kilometer instead of multiplying by 20 kilometers per hour, and that's going to produce the number $5.12.5 per kilometer. So to convert my rate of dollars per hour into a dollars per kilometer, I need only multiply by the reciprocal of the given velocity. So here's what I can do. Looking at just with labels, the cost, which will depend on my velocity, measured in dollars per kilometer, can be calculated by v squared over 10 plus 62.50, and that's the given information, dollars per hour, multiplied by 1 over v, that'll be hours per kilometer. If you strip away the labels, you just get the equation v squared over 10 plus 62.50 times 1 over v. If I distribute the 1 over v, I will get this more simplified equation. And to put it into terms that will make calculus easier, I've got 1/10 v plus 62.5 v to the negative 1. Now this is a function that will express the cost as a function of velocity in dollars per kilometer. All we need to do is to minimize the cost per kilometer. That is, we need to find a speed that will give me the smallest possible cost. And with my unpacking example, when we go 20 kilometers per hour, our cost is going to be $5.125 per kilometer. Can we get a lower cost out of this? You can guess and check your way. Obviously, we can look for a graph and see what the graph says. In fact, I have one right here. But how does the calculus bear that out? So here, I take the derivative of the function, which is going to be 1 over 10 times 1, then minus 62.5 v to the negative 2. That's just using the standard power rule. I'm interested in when the rate of change in the cost is 0. That is, when is the cost per kilometer going to stop decreasing and start increasing? That's where my minimum is going to be located. And so, in other words, I need to solve the equation 1 over 10 equals minus 62.5 v to the negative 2 equals 0. So the rest of this is algebra. I add 62.5 v to the negative 2 to both sides, bringing the v squared down to the bottom. Then I cross multiply to get v squared equals 625. V equals plus or minus the square root of 625, and we're going to keep the positive. We have 25 kilometers per hour. Go back to my cost function, and the cost at 25 kilometers per hour can be calculated with these numbers, and that turns out to be $5 per kilometer. And that's borne out on the graph. The minimum point on the graph is 25 kilometers per hour, producing $5 per kilometer. And what's interesting here is you can see when I checked at 20 kilometers per hour, our cost was only slightly bigger than $5 per hour. But here we have a minimum value that's even better than that. So we can go for hours and hours and hours, saving 12.5 cents at a time.